All right, so I'll check out Piazza in a few minutes when I'm done with the lecture. Bring it on. So today we're going to be talking about that introductory chapter on data structures. So this is going to be reorganized in the next edition of the book, and so I have the PDFs, and I figured I might as well use the shiny and new material. So you'll find it in the content area. I'm sure you have found it by now in the content area of Desire to Learn. So collections. As I'm sure you know, lots of times you need to collect a bunch of objects of the same type in your program. Like when you have a quiz, it's a collection of questions. When you have a calendar, it might be a collection of appointments and so on. And so you've learned in 46A you can use arrays or you can use array lists. And so ArrayList is kind of it's a pretty good collection. If you don't have any other idea what you should do, ArrayList is a good all-around collection. But sometimes there are situations when ArrayList is just not good enough and where you can do better than that. So we'll go through the various collection types that Java provides. And Java actually does a very nice object-oriented approach that there is an interface for each collection type, and then there's one or more classes that implement that interface, as we'll see on this picture here. So you'll see there's an interface called list, and there are two different implementations, array list and linked list. There's an interface called set with two different implementations, hash set and tree set. And then there is an interface map with hash map and tree map. And there's a bunch of others that we're not going to be getting around to, but these are the basic ones. So when you look at collections, the first question you need to ask yourself is, when you're collecting some items, do you care in which order you get them? So look at a quiz, for example. So you want to model a quiz. Do you care about the order in which the questions are kept? And there's really no one answer. You might not care at all. You might say, well, if they just get presented to the student in some random order, that's just fine. Or you might want to have them sorted from easier to harder ones. And then you would care about the order. So it really depends on the kind of problem that you have. If you care about the order, you have to use something that's called a list. So a list will let you maintain a sequence where whatever order you put the things in, that's the order that they're going to stay. So here, the little picture here that should help you is here this dictionary that has the volumes arranged in order. Sometimes you don't care about the order, and then it's sometimes advantageous to use a set because sets are faster. So if the order doesn't matter to you, then consider using a set. You get some extra speed, and we'll see that in Thursday's lecture. And then there's another situation where you don't care to see all of the elements at once, but you only want to see one of them at a time. And the two disciplines that we encounter on, I guess, the Tuesday after the break are stacks and queues. In a stack, you can put an element, and just think of the stack of books. You just pile one up after another, and then when you retrieve them, you're not allowed to pull one out in the middle. You can only get the one that's on top. Whereas, of course, with a list, you can say, give me the fifth element, and it'll give it to you. Or you can say, remove the fifth element, and it'll slide all the others back. With a stack, that's not permitted. You can only go and get the top one. And there's some algorithms for which that's a pretty good abstraction. A queue is similar to that, except that you add in one element and you take out on another. So we'll see some applications of those two data structures. And then the maps. Maps are a little different. They're not really a collection. In a collection, you just dump objects into the collection and you get them out in some discipline. But a map it's an association. So the example that's I think is pretty obvious is here, where you have the ISBN code, which is a string, and you would associate that with an object of class book. So So the object of class book might remember the author, the number of pages, or maybe even the actual contents of the pages. And so a map, instead of having a first, second, third, fourth element and so on, it has an association where you can look up a book by its ISBN code. So that's kind of the landscape of the various collections that we're going to be looking at. Now, all of the collections, except for maps, which are different, all of the collections have a common superclass called collection. And so what's nice is that many of the methods are in that common superclass, so you only have to learn them once. So over here, I'll just walk you through this code here one by one. Over here, I'm making a new array list. And if I like, I can say, because an array list is a subclass of collection, I can just store it in a variable of type collection. I can also do that with a different one. Here I have a tree set, and I can also say that's the collection. Now, what can I do with a collection? There's some things that you can't do because sets and array lists are more specialized, but there are a whole bunch of things that you can do already. For example, every collection has a method called size that gives the number of elements that's in it. And it's always called size, so you don't have to remember that. There's an add method that adds a string to the collection. Now, where it adds, that depends on the collection. If you add something to a queue or a stack or a set or a list, every one of those collections has its own idea what it means to where to add something, but they all do have an add method. So with an array list, as you know, when you call add, it adds it at the end. With a set, when you call add, it just adds it wherever it likes where it can find it easily. So here we're adding a bunch of elements to the collection. A collection by itself has no way of saying add something on spot 5. A list does, because that's what makes a list, that it has an ordering of the elements. But a collection doesn't. Now, anytime you have a collection, you can call toString, and then you get a string in this characteristic look, the way you have open and close brackets at the end, and then a comma-separated list of the toStrings of the elements. So anytime for debugging that you want to know what's in a collection, doesn't matter which collection, you can just call toString. And so when you just print out the collection, then it automatically invokes toString action. All collections have a method remove to remove an element, and then it'll try to locate that element and remove it if it's there. And these methods here return true if the removal was successful, and they return false if the removal wasn't. So it's not an error to remove something that wasn't there. Remove will just say, well, I didn't manage to do it. Now, that's actually not quite true. Some collections have remove defined to throw an exception. So remove is kind of technically there, but if you were to use it, it wouldn't work out. So for example, it's not really legal to remove something from the middle of a stack or of a queue, and you shouldn't be calling remove in those situations. Now finally, when you want to visit all of the elements in a collection, the easy way to do it is to use the enhanced for loop. So when you say for and then some element colon and then the collection, then you get to see the first element, the second element, and so on, just like you did for array lists. So once you've seen this for array lists, it's no surprise to you. It works for any old collection. There is a second way of going through a collection that we're going to be seeing in a minute, where you ask the collection to give you an iterator, and then the iterator can be used not just to visit all of the elements in a collection, but also to modify it. So this first form of visiting is only good for seeing what's inside. It can't edit the enhanced for loop. But this form here, you can modify the collection, and we'll see that with a linked list in just a minute. So all of these methods work for all collections. You've seen them all for arrays, for array lists, I should say, and so it's kind of nice to know that they always work. All right. So one of the things that's always an issue with having choices is you have to sometimes make one. So let's practice that. So in this particular situation that I'm outlining here, I'm asking you which data structure from the introduction that you've just listened to, which data structure is the most likely choice for these. So set that up. All right, so we have a majority answer, but not a unanimous one. So let's see. So if we had the books as a set, then that means we would put all the books like in a box, and then we would read them in random order. And I know it's social science, maybe that'll work. So with the queue, the way that you would read them is as they get assigned, they would get into the queue, and the first one that you would read is the first one that was assigned. The second one you would read was the second one that was assigned, and so on. What could happen, of course, is that they pile up in the queue, that maybe the professor puts them in there faster than he can read them, but you would read them in the same order in which they were inserted. With a stack, and that was the majority answer, with a stack, you would read the latest one first. So whichever one the professor assigned latest, you would read them first. And if you ever got to the earlier ones, eventually you would read them all. But whatever they put on latest, you would read first. And maybe from a student's perspective, that's not an irrational strategy, right? Because if the if it was assigned weeks ago and you never got around to it, maybe it's no longer relevant. And finally, with the map, that probably wouldn't really work because the map needs some kind of a key, and we don't really have that. So I think that a queue seems like the most likely one, but if you wanted to make a point of saying that you do what you can, but at least last in, first out, then you might want to pick a stack. So that's a bit of a judgment call. I always ask that same question when I process my email, and I have like 200 messages in my inbox. Which way should I answer? Should I answer the oldest first or the newest first? And I actually do it as a stack. I answer the newest one first, figuring that way at least a few people have the illusion of getting an instant response. And those people who are like a few weeks back, well, that's pretty hopeless anyway. So that's the difference between these. All right. Now on to the first data structure that's a bit different from anything that you've seen in the linked list. So in an array, as you know, you just have a sequence of values, packed after another. And the disadvantage of an array is insertion and removal in the middle. So if you consider, this is not working. If you consider your typical array like this, and now you decide that you need to insert another element here, well, then you need to move all of these elements over, and that takes time. If the array has n elements, that takes O of n time. So a linked list avoids that by saying we're just going to store every single element in a separate object, in a separate blob. These objects are called nodes. And each node is just linked to the next one and to the previous one, hence the name of a linked list. And so when you insert something, then you make a new blob, that's the one over here, and you update the links that go to the left and the right. And so if you think about it, here you had to update 4 links no matter how many elements are already in the linked list. So you might have 1,000 elements in the list, but to add a new one, it takes a constant time. You just update 4 links. Same for removing. If you need to remove an element, you need to reroute the neighboring links so that this one now points to the one that's now going to be the next one, and this one points to the one that's now going to be the previous one. And then instantly the one in the middle is forgotten. And so again, removal means no movement except for rerouting a fixed number of links. So that's nice and fast. And that's the reason that linked lists are an attractive data structure in this case. So you would use a linked list if you often need to insert or remove in the middle of the data structure, and you don't want to pay for moving all of the other elements. So let's look at what you can do with a linked list. So you can construct one, then you get an empty one. There are methods called add last and add first, where you can add at the tail or at the head of the linked list. Notice that there is no method for adding in the middle. So if you wanted to add the 10th element of a linked list, that's not so easy to do because you would have to go to the beginning and then you would have to skip over 9 of them before you have a place for that. And that would be slow. That means you would have to do that skipping process as many times as you have your subscript. So inserting in the middle is not something you would want to do in a linked list. There are ways of doing it that we'll see in a minute, but it's not something you generally want to do a lot. So you can get the first and get the last element, but again, you don't really want to take a linked list and say, give me the 20th element. Because the 20th element, it has to skip past the first 19 elements to get there. Whereas with an array, the address calculation is instantaneous. With an array, there's a starting address here, and now if you want to know the 20th element, you would add 20 times the size of each element, and you would know which address to look up the 20th. So it would be done in constant time. There's no need to skip in an array. You can instantaneously get any element. So for that reason, arrays are sometimes called random access, because anything, no matter what, can be accessed instantly, whereas linked lists have sequential access. You have to first skip past the k-1 elements to get the kth one. So here again, get first, get last. We get the first and the last one right away. The other ones we don't. We can remove the first or remove the last one with remove first, remove last. To remove in the middle, it's not so easy. And then we can, if we wanted to do surgery somewhere in the middle of the thing, we get one of these iterators. and that's going to be the topic of the next slide. All right, so an iterator is an object that's associated with the linked list, and you can get one by asking the linked list. So you say, hey, list, give me a list iterator. You call this method, and then you get that iterator object. Over here, it's shown as this little red line, and so it indicates a position in the linked list. Well, actually, conceptually, it's best to think of an iterator as a cursor in a word processor that sits between positions. So when you type up something in a word processor, you'll notice that little vertical bar that can move back and forth, and that lets you specify a position between two elements. When you first make an iterator, it symbolizes the position before the first. Then when you call the next method, it skips over the first and moves past the first element. When you call, well, okay, and here now we're calling the add method, then the add method will add an element before the bar, just like what would happen in a word processor. In fact, just for grins, let me run a word processor. Do I have one here? Let's crank up the font size here. So here you see this thing, that's the iterator. And now if I were to insert something, now I'm going to insert the X. Notice that it gets inserted before the cursor position, and now the cursor is after the X. And that's exactly the same way that that an iterator works in a linked list. So here I have my the bar. Now I inserted the J here, and it gets moved before that. So the next method returns whatever it is that the cursor just jumped over. So if I go here, if I make the beginning here, now I call next, and you see the cursor jumped over the D, and the D gets returned by next. So if I keep calling next, 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 each time it'll remove, no, it'll not remove, it'll just it'll yield the element that I traversed. Now you can also update an element, and updating is a little bit funny. Let's say I wanted to change, say, this H here into an X. What I would have to do is I would have to call next once to jump over the D, then I call next again to jump over the H, and then I call set. Set will replace whatever element I just jumped over. Now, you want to know how many times you can jump, and so you call has next. So you would generally call has next, and then next, has next, next, has next, next. And over here, has next would return false, and you wouldn't call next. If you did, you would get an exception. Iterators can move in both directions. They can go next, and you can call previous to go to the previous direction. I don't think we're actually going to take advantage of that in this course, but the ability is there. So we have adding. We have removing. Removing is a bit weird. Removing removes the element that you just jumped over. So if I were to use the word processor analogy, if I wanted to remove the B, what I would have to do is I start at the beginning, I jump over the B, and then I hit remove, and then it's gone. That's not how a word processor works. And in fact, removal is always a bit of grief. It's not the greatest way of setting it up. The way they set it up like this, though, is it makes one situation pretty easy to implement. Sometimes you want to traverse a linked list and remove everything that fulfills a particular condition. And then the code that does that is the following. You say, while there is a next, now it's safe to call next, and you get whatever it is that was under the iterator. And now you check whether whatever it is that you got fulfills some condition. And when it is, then you can call iterator.remove. And that'll remove the thing that you just skipped over, the thing that fulfills the condition. And then it arranges everything just so that when you call has next and next again, it picks up after the thing that was just removed. So that's obviously going to be something that'll come in handy for one of the homeworks. All right, let's just try this. For this, I'm sure you're going to need a sheet of paper. So here I have a set of confusing directions, and I'm asking you, when you apply that to the linked list here, what is the result? I guess I should say that add is the same thing as adding at the end of the linked list. All right, let me set up the question. Aha. All right, let's see. So we start at the beginning. We call next. We call next. That skips over the F, skips over the R. Now I call remove. That removes whichever one I just skipped over. Now I call next. That skips over the E, so now I'm here. And now I add the X. That adds it before the cursor, just like a word processor. So it would be FEXD, which is answer number 2. Let's see how people are reacting to this. And so, okay, so people get that. All right. All right, so that's what you kind of have to know about the basic operations of linked lists. We'll be having a few exercises with them, and in the next chapter you'll see how to implement them and how efficient they are. All right, so let's go on to the Piazza questions that you guys had before we do the lab. Can I explain homework 6B? And the answer is yes. Moving on. Can I explain more about the partition method and what I should do in the if statements? All right, so let's pull that up. This is homework 6. So the basic idea here is that you have this array, and let's first of all look at the classical quicksort, the quicksort that you find in the book. In the classical quicksort, you have a pivot, and the pivot is the same either way. It's the first element, and then you partition the array into regions where the first one is greater or equal to the pivot. This one here is less equal to the pivot. This one is greater or equal to the pivot, and then you have this unknown region in the middle where you don't quite know what's happening yet. And you have an index I and index j here. And then you deal with the various possibilities that could happen now. So if the element here is less or equal to the pivot, then all you have to do is add it here and update I. Similarly, if this one here is greater or equal than the pivot, then you can just move j to the left. But now let's say that this one here did not oblige. Let's say this one here was greater and this one here was less than, then you might have to swap those two and advance I and j. There's a bunch of cases, and you can find those in the book. The outcome of all of this is that in the end, you're going to have I and j cross over. So I is going to be here, and j is going to be to the left of it. Everything here is less equal p, and everything here is greater or equal than p. So when you look at the source in the book, you'll see those 2 pointers, or these 2 indexes I and j, moving inwards until they cross over, and they will affect there's various situations that will all be done by moving the element either to be a part of the left group or a part of the right group. So it'll sort them like that. So that's not quite what we want. What we want is an arrangement where we have everything that equals the pivot here, everything that's strictly less than here, everything that's strictly greater than here, and again a bunch of things that are equal here. And so again we're going to be having the unknown area in the middle where we have indexes I and j. I moves to the right, j moves to the left, and then we need to figure out how do we update them. So let's say I'm going to look at this element here. And so what can AI be? It could be equal to the pivot, less than the pivot, or greater than the pivot. And now we need to figure out what to do in each of the cases. Let's pick the easiest case, that it's less than the pivot. In that case here, my life is really easy because all I have to do is I have to increment I. Then I points to the next one. Now I know that this thing is less than the pivot, and it falls right into the region, right? And this one here moves over, and I'm done. Now let's say that it's equal to the pivot. So this one here, that means I want to somehow swap it into the equal area here. And the way to do that is you pick the first one that's not equal, and then you swap these two. Now this one here we now know is equal to the pivot. That extends the equal area by 1, so we better update the pointer there. But now we've swapped it into the right place, and we can increment I. So swap into the equal area and I++. And now the third case is, what if it's greater than the pivot? Well, at that point, now let's look at what happens at j here, because we have similar situations. So if aj, if that equals the pivot or it is greater than the pivot, then you do kind of the same thing. You take this thing and move it somewhere here. And now the only situation that you need to do something different is if you have a greater here and a less than on the other side. So if both of these are true, then you swap the positions at I and j. And then, because then the greater one ends up here and the lesser one ends up here. So that's the algorithm here. And so in each step, there's 5 possible cases, and you just need to, by some amount of swapping and incrementing I or decrementing j, bring it into the same picture as you had before, except with that new element taken care of in I and j, and maybe these indexes here moved to the right places. Now, what I would actually do to program that, because it's a fiddly thing, right? I would make myself a test case, just like you've learned last time. I would, in fact, make a JUnit test case that sets up an array and that checks that property afterwards. And that way you can see that you did it right. Because certainly it's easy to get things wrong there. I'm sure that when I did it the first time, I did something wrong. So let's see what the question was. So he's the question asked, am I supposed to swap the elements? Should I move the regions? And the answer is all of the above sometimes. So there are these 5 different cases. So you can easily take care of if AI equals P, if IA is less than P, if AJ equals P, if AJ greater than P. In the leftover case, you have to do swapping. Actually, in 3 of the cases, you have to do swapping. You swap if the thing here, needs to be put over here. That's the swap that I indicated here. You swap if the thing here needs to be put over here, or you swap in that third case that they're both out of order. So in 3 of the 5 cases, you need to do swapping. In 2 of the 5 cases, all you do is you extend the boundary of I and j by just moving I or j inwards. So you really do need to think of all of the 5 cases, come up with an example for each of them, adjust the indexes, do the swapping, and you'll be good. I can't give you any other shortcut except to give you the solution. Now, remember, after you've done that, you need to do another step. You need to rearrange them so that the equals fall into the middle. So before we had the equals here, we had the less thans, the greater thans, and now it's fully set. There's no mystery area in the middle. So we have these 4 areas, and now we need to rearrange it so that all of these here go over here, all of these go over here, so those are 2 loops. How do you know how many elements here are? Well, you're given the indexes. I don't remember in which form. In some fiddly array where you're given the last element that's still equal or the first one that's in the less than area. I don't remember. And you just have to figure out what that difference here is. I'll say something about that in a minute. And the same thing on the greater sign. So you have to have a loop that copies them over. So you can do this one with a loop. Or there's actually a method called arrays.copy No, you'd have to use system.array copy. Just do a loop. It's not worth doing the other one. Just do the loop. And then how do you put the equal ones in the middle? There's a danger, of course, that by having done the first, by having moved the less than to the left and the greater than to the right, maybe you've now overwritten all of the equal ones. Maybe there aren't that many of them after all, but you know what they are. They're all the same value, so you can take this one, pull it out to somewhere, temporarily hold it, and then you can just copy that one into all of these. So, 3 loops. Not nested loops, just 3 loops, one after another. And so the only real thing that you need to figure out is how to deal with those fiddly arrays, indexes. So let's have a quick look at those indexes. So I had to draw a picture of this because they were just so tedious. So here we're getting 3 indexes, B0, no, we have 5 indexes. We have from to B0, B1, and B2. So let's so there's some other stuff that goes on outside that we don't care about. Here's from. And notice that they're kind of asymmetric, that that from points to the first one, to points to the last one. It's not the same thing that you would have with substrings. So how many elements are in here total? Yes, so in this range between from and to, how many elements? 2 minus from plus 1. Okay, you simply must know this fact, that when you have 2 indexes, the starting and the ending index of a range in an array, that the span is not 2 minus from. That would be if 2 was pointing to the outside, but it's 2 minus from plus 1. Let's have a quick example. Let's say from is 10 and 2 is 20. In this case, that would be 20 minus 10 plus 1, or 11 elements here. Because it's 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Let's see, are there really 11? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 elements. So, that's a basic fact here that you'll need whenever you want to write one of those loops. You need to be really careful about that extra plus 1 when you have these symmetric bounds. All right, now let's see what are the other values. Now we have values B0, B1, and B2. And now we need to be really careful where they fall. So the equal ones have positions from to B0. So I'm going to carefully draw this line here after the B0. Then the less than ones have positions B0 plus 1 to B1 minus 1. So I'm going to carefully draw this line so that it comes before the B1. The greater ones have B1 to B2 minus 1. And then the other equals have B2 to 2. So that's here. And it seems completely arbitrary, and it is. It's just whatever because there's no one symmetric way of doing it. So I just, whatever worked for me the first time I codified so that we all do the same thing. So let's see how many elements we have in the various subregions. So over here, how many elements? All right. Is it from minus b0? Is it from minus b0 plus 1? Is it b0 minus from? b0 minus from plus 1? b0 minus from minus 1? b0 minus from plus 1. It's the same as we had in the big one. All right. How about this one? Is the same thing, right? So this is now 2 minus b0 plus 1. And the other ones are a little trickier. So let's look at this one here first. How many? It's b2 minus b1. And there's no plus 1 because the b2 stretches to the outside. How about this one? Well, it's going to be something like b1 minus 0 minus 1 because one of them is still to the outside. Now, it's actually a good idea to add up all those 4 to see that we get the correct count again. And if you do that, so then the b0s cancel. I'm just going to add them all up and see that everything cancels out. The b1s cancel. This plus 1 cancels with this minus 1. Oh, this should have been a b2 and not a b0. And then it cancels against this one here. And then what's left over is minus from plus to plus 1. That's good. That's exactly what I had over here. Now, you might say, oh my God, he's doing all of this algebra. But the reason I like to do the algebra at this point on a piece of scratch paper is if it now works out, then that's great. But if it doesn't, then I want to find out now rather than when debugging. You had a question up there?
Why is the less than b0
All right. So let's look at that under a microscope here. If this thing was here as a thought experiment, then the distance would be b1 minus b0 because you have the one bound in the inside and the other bound in the outside. But this one was one further to the right, which means it's actually one less than that. Now, the other way you can figure this out, if you find this too abstract, and I highly recommend it, is you could simply come up with some value. You could say, well, let's say this thing was 10, let's say this thing was 12, this thing was 15, and this thing was 17, and this thing was 20. Then let's see, here we would have the numbers 13 and 14. And now you can try it out. 15 minus 12 is 3, minus 1 is 2, and there's only 2 values inside here. And it's always a good idea to do that as a check, because if it works for a specific example and you hit it on the nose, then you can't be off by 1. So you can always nail down off by 1 errors by running through one specific example. And oftentimes it's easier on the brain than to try to do some kind of general reasoning. But it is super, super useful to do this. Get out a piece of scratch paper, and write these things. Make a little picture like that. Write the lengths of each of these intervals. Because now that you have the length to write the loop that moves these over to the left, remember we have to move all of these over here. You know how many there are. So you can have a loop counter. And finally, to fill in the ones in the middle, now, it's kind of a nasty arithmetic. You have to take this number, you have to take this value, add them up, and now that gives you the loop counter for filling the middle. So I remember I was solving this thing on the train, and I was a little reluctant to get out a sheet of paper, and I wasted 10 minutes of my life trying to do it without it, and then I gave up and I drew the picture. All right, so going to draw that picture. It's not really an incredibly tricky assignment once you know what it is that you need to do, and once you draw the right picture. And so hopefully the movie will come out and you can review that. Someone said he or she brought this to the tutoring lab, and the tutor had no idea how to do it because it was not one of the standard problems. But in all fairness, even for a tutor, it would take them 10-15 minutes of concentration to figure it out. So if you were the first one where the tutor saw that problem, the tutor would have to sit in a corner for a few minutes to have a look at it. It's not a totally obvious problem, but it's not rocket science either once you start wrapping your head around it. So if you have more specific question or some code that doesn't work, by all means bring it on. Someone was in my office hour with some code that didn't work, and I said, why didn't you put it on Piazza? And that person said, well, I might have given away valuable information. It's news to me that code that doesn't work is valuable information. So by all means, if you have anything at all that doesn't work, put it on. It's more trouble for someone to isolate the good parts than to just solve it themselves. And people have been very, very good about this, and I'm really grateful. I was out of town over the weekend, and when I came back on Sunday night, there were a whole bunch of problems that people gave good solutions for, and I didn't have to do it. All right. There's a follow-on question? No. Linked list remove versus array list remove. What's the difference between them? All right, so that's a great question. And so the short answer is, from an abstract point of view, nothing. So if you have an array list like this, and now you have a linked list, and now let's say we want to remove the fourth element. So we call remove 4. Then for a linked list, what has to be done is it has to locate that element, so it has to follow these links, and then it has to disentangle them here by rerouting here, and then this element will be gone. For an array list, it can, of course, immediately access the fourth element, and then what it has to do is it has to shift these 3 over. The ultimate behavior is the same. Afterwards, the fourth element is removed. But the way it's removed is completely different because they're different data structures. So from an outside observer point of view, if you just ask what are the elements now, then either way it's the same. From an implementation point of view, they have very little in common. How about efficiency? Removing in this out of an array, as we'll see later, is an O of n operation if the array has length n, because you have to move that tail up. Removing in a linked list in this situation is also O of n, because you have to first skip past those other links, and that would be on average n over 2 of them. So the performance is even the same. On the other hand, if you have an iterator, and that iterator works its way through from the beginning to the end, inspecting one element at a time, then the removal with an iterator, if you already have the iterator pointed to the right place, let me draw one in some distinctive color. So if I have the position, over here I would have it with an iterator, and over here I would just have it with an integer index. If I have the position, then removing it's here, sorry. If I have the position, then removing out of a linked list is instantaneous. Just update the links to the left and the right. If I have the position in an array, then removing still takes plenty of time because everything that comes after I have to move. So in the homework, for the draft, since we had not yet covered the iterators, I said just use the standard remove method, even though it's not what you would normally do in a linked list. But now that you're done with the draft for the final version, you can really use the iterator. And so the grader will, of course, have a look at your code and see that you really did do the iterator. All right, did we beat those to death? Okay, so here we have a follow-up question. When I find an element that's equal to the pivot, this is a great question. Too bad I can't give a great question for a follow-up. When I find an element that's equal to the pivot at I, is it better to just swap it, or is it better to insert it and shift? And so the intuition here is shifting is always bad. that shifting always costs you whatever the length of the shift is to move it to where you need it to. It's always a loop that has as many iterations as the area that you want to shift. Where swapping only involves two elements. Swapping is fast. So the idea of partitioning is you want to use swaps and not shifts. So because swaps are fast, so that you get things not in the correct sorted order, but just into a better order. So remember, when we do the partitioning, we're not aiming for perfection. We're not saying that the stuff should be sorted. We say, if we just use plain old quicksort, we just want these to be less equal and those to be greater equal. They can still be at completely random orders. And so when we're in the situation that I have one in the middle that I don't yet know what it is, then well, actually, let's do it in the example that I said. I think that'll make more sense with the question. So we had this way. So in these two pieces, we don't care about the order. So any order is okay with you, as long as they're all less than or greater than. So now I have this mystery one here, and I wonder what to do with it. And so I definitely want to swap it over here. I do not want to move this area here. The swapping will, in here. In here, in here? No, that was right the first time. The swapping will preserve it because now this one here, it was equal, right? So this one now becomes equal here. And then what I swapped out was a less than, and so that means everything in here is still less than. Yes, it's been rearranged, but the order never mattered in the first place, so the fact that it's now rearranged is immaterial. So you definitely, you want to swap. Otherwise, the algorithm will act poorly. And I thought I resolved this. Okay. All right, so let's move on to the lab. So today you should finish lab 4. It's the last chance for lab 4. And there's a lot of stuff in here. If you don't get it done, you don't get it done. So what would be really, really useful is if you get to testing exceptions, because that is something that happens a lot in real life. So try to fight your way through this here and do as much as you can of the rest of it. The other thing I want to say, and I'm going to say it a couple of times, for Thursday, the lab requires a somewhat non-trivial installation. And I want you to do it before the lab. And that doesn't mean in the lecture during the lab, but do it tomorrow. I should actually change the quiz and ask a quiz question before about it. I might do that. So do this installation before the lab. It's a little bit tedious. It depends on which operating system you use. Particularly the Mac users are going to find that it requires you to install a bunch of stuff that a casual Mac user will have never seen. So the Mac has these two faces that, on the one hand, it's a nice system for a user who doesn't want to deal with Windows, and it's easy to use and stuff. But it also is a development machine. So Apple has this package called Xcode that contains all of the development stuff, and you need to hunt it down. It comes on that CD, or I guess nowadays it's a DVD. It comes on the DVD that you lost 5 minutes after you unpacked your Mac. And so you probably need to download it. And it's a huge download. So download that. And then you install this thing called Mac Ports that a bunch of volunteers did to port a whole bunch of useful software on the Mac. And it'll compile absolutely everything. So it'll compile what we need, this thing called Mercurial, and all of its dependencies. It takes several hours. You can still use your machine in those several hours. It runs in the background. But make sure to do this before Thursday so you don't look like an idiot on Thursday. All right. All right. Do not do that. If you follow the instructions the way that I had, that you use only in Xcode? Yeah. Oh, Xcode, that's fine. Xcode you can get from the App Store. Yeah, go for it. But don't don't bypass the Mac ports thing. Because there's 10 different ways of packaging this Mercurial stuff, and I just can't possibly help debug if you just choose to your own path. Also for the Windows users, I know that you can get Tortoise and all of these other various packagings of Mercurial. Do it the way that I said. Use Cygwin and download it in that way. It will work, and that way we'll all have the same experience, and when something doesn't work, we can get to debug it. All right, so yeah, just install that, and then we'll have a happy life on Thursday. Also on Thursday, the buddies will change. There was a bunch of requests for buddy changes, and then I went overboard and changed a whole bunch of different assignments. Today, it's still the old buddies. On Thursday, a new lab, a new life. It'll be the new one. All right.